Okay. Okay, so I want to welcome everybody to the second seminar of the series. Just want to recall that this is a virtual seminar series that has been started by the SIAM Activity Group. We had an inaugural talk by Matt Sooner like about 2 weeks ago, and want to remind a little bit the rules of the seminar. So essentially, starting from this lecture, we have decided to promote to panelists all members of the CFIN editorial board, plus 20, roughly 20 other people that are selected by the host, which in this case turns out to be me. I've already added a few of you. So if you are there, it means that you have been promoted to panelists. And for the remaining, and we will try to rotate. So every seminar, there will be different attendees that will be promoted to panelists, so that basically we give an opportunity to everybody to see who is around. So that's the benefit that you get when you are in the panel list. And also I want to mention that if you have any question during the talk and you are not a panelist, please ask the question through the public chat, or ask the question directly to me, sending me a private message. And then I will collect these questions, and at the middle of the talk, around the middle of the talk, I will like interrupt briefly Blanca, and I will ask like the questions. I will pose her the questions that have been asked, or I will let you directly speak and ask the question. Okay, so that's it for the series, like for the roots of the seminars, the online seminar series. Now I want to switch and introduce the speaker of today, who is Blanca Horvath. And Blanca is a lecturer in financial mathematics at the King's College in London, and also a researcher of machine learning in finance at the Alan Turing Institute. She also has an honorary lecturer position at the Imperial College London. And she is interested in a lot of problems related to machine learning, non-Markovian models of financial markets, rough volatility, and so on. And she was recently awarded the Rising Star Award from the Risk magazine. And yeah, in terms of education, she got her PhD from ETH Zurich, and she has a diploma in mathematics also from the University of Bonn. So without further say, I want to leave the floor to Blanca, and looking forward to a very exciting and interesting talk. Yeah, Blanca, the floor is yours.
So thank you very much, Agostino, and thank you to Agostino, Igor, Sebastian, and Ronnie for setting up this series. This is really a great honor to be here, and especially it's a great honor to be speaking after Mete Sona last week, who has set the bar high, and also after Mathieu Rosenbaum last week. So I'm really looking forward to this, and thank you very much again. I will start sharing my screen. Which should hopefully be visible now. Is it all good?
Yeah, it's nice.
Okay. So this will be about a data-driven market simulator for small data environments. And this was just a second. This is based on joint work with Hans Buehler, Terry Lyons, Emmanuel Perez Arribaz, and Ben Wood. The ideas of the work in the beginning originated from my time that I spent at JP Morgan just before joining King's College, and were motivated a little bit by the considerations of deep hedging. And then they flourished further in discussions with Terry and Emmanuel. So let me start by a very quick recap of market simulation and mathematical finance, because this is not something that's new, in fact. But the horizons of mathematical finance are now and have always been transforming towards more and more accurate models. So models that can fit data more and more accurately. And mainly these changes were made possible by the increase of computing power. The question is whether these changes are also necessary, but we will come to a couple of use cases later. So classical models, as we know them very well since several decades. They were historically simplified but tractable model of reality, but they had the advantage that they had few parameters. The role of the parameters was clear, but also the properties and limitations of the model was well understood. We often had numerical and asymptotic approximations, often with a full error analysis available. And when we speak about limitations of the models, I think this current time is actually a very good time that demonstrates that models can really be of a certain limitation and not necessarily predict extreme scenarios as today. But on the plus side, we had always well-established risk management and model governance rules. Now, even there in these classical models and historically established models, there was a trend towards more and more complex models. And there was somehow a race towards more accurate reflection, for example, of stylized facts. More complicated models were introduced to fit option prices or path-dependent considerations, or to just consolidate modeling of different markets, such as P measure and Q measure considerations. And sometimes already there, we allowed for some kind of trade-off between this modeling accuracy and giving up some other positive aspects, such as tractability or control over errors or interpretability. And okay, classical, or let's call them also even neoclassical models, the simplest of them was the Black-Scholes model, and then building up diffusions, jump diffusions, stochastic volatility, LSV, multi-factor models, and so on, more and more complex models, and letting more and more accurate depiction of the markets. Now, on the other side, completely independent from finance, there were deep neural network-based generative modeling approaches. The question is, if we want to go down that road, and if we want to go further on in this trade-off of giving up tractability perhaps, or giving up perhaps interpretability, would we want to adapt these generative models to finance? These models are usually called data-driven, but not often does it really explain what it means. Well, several authors agree on this kind of interpretation of data-drivenness. There's no a priori assumption on the distribution of a stochastic process in the beginning. However, if we say that they're non-parametric, I would tend to disagree, because if I put down here a very simple case of a feed-forward neural network with R hidden layers, input dimension, output dimension, activation functions, and here denoting the nodes on each hidden layer, we see that these nodes or parameters are actually there. So non-parametric is actually not quite right, but we can at least say that they're very, very flexible. And since the number of hyperparameters and parameters is not limited, we can actually approximate extremely closely these models, with these models. But they were originally developed for static problems. And it turns out that as well as they work for static problems, the adaptation for financial time series is absolutely not straightforward. So I will be speaking about this later. And this is really actually a challenge. And there's several different approaches to that, and really an ongoing work to figure out what kinds of ways to tackle this are the best. Now, when we speak about market simulation and market generators, market simulators, I do also want to mention 1.5, where that lies somewhere between 1 and 2, so hence the numbering. And this kind of mixes both worlds, so the positive parts of both worlds, in the sense that these models extend or augment currently prevalent stochastic models in many different ways. And these are also very promising as a first step. So they are more adaptive to market dynamics, so they can build in this possibility that we have larger computational power. We are able to fit more closely to data because we're able to compute more closely. But since they are built of building blocks of classical models, they are easier to understand and easier to risk manage than fully data-driven models. And there are quite a few people working on similar things, but we have made a first step towards such mixture models in the paper Deep Learning Volatility, where we took a mixture of 2 or more stochastic volatility models and just viewed them as if the mixing parameter is just one more parameter to calibrate, and then calibrated them to market data. Now, clearly, this has its disadvantages, or it has its limitations so far, making it so simple, because if we're just calibrating to option price data, we have infinitely many possibilities to calibrate to, so this is not the end of the story. But this is one way of doing so. But there are more flexible mixture models, such as neural SDEs, where one can parameterize these diffusion parameters in a more flexible way. And then there's optimal transport approaches, where one can interpolate in a smart way between model-specific and model-independent settings. This is work by Jan Obloy, already originating in 2018. And then there's also very promising non-parametric mixtures. One of them proposed by Emmanuel Perez Arribaz and Christophe Alsaivi, where one can have mixtures that are interpolated using signatures, which is a non-parametric way of looking at models. Or one can mix points 1 and 2 directly by mixing classical models with data-driven approaches. So all of these are very promising and very interesting. However, just having mentioned these, we will go directly to point number 2. Keeping in mind that all these mixture models are maybe for now a very promising next step towards more flexible modeling. So, oh my God, just give me a second. There it is. So, these generative models were around for a long time in other AI applications. Should we adapt them to finance? These generative models can be seen as some sort of transformation between a source distribution, which we call mu now, be it a uniform distribution or a normal distribution. And this can be trained using some sample data to some target distribution. And if they're trained well, if enough samples are provided, then these can, this target distribution can become similar or even indistinguishable in some kind of probability metric from the observed ones. And we refer to these as data-driven because there is, again, no assumption made on the latter distributions. So in some sense, we can call them as a transport, or see them as a transport map. It doesn't really matter whether we're starting out with one distribution for another. This just provides a source of randomness, and this transformation from the original source of the distribution and the target distribution is what's learned. And this is how neural networks are used in their typical framework, as approximating transformations from one distribution to the other. So right now there are several popular deep neural network-based generative models around. Historically, the one that was longest used is the restricted Boltzmann machine, which has just two layers, a hidden layer and a visible layer, and the distribution is learned by passing through the hidden layer and the visible layer several times until the target distribution is learned. The advantage of this restricted Boltzmann machine is that it has a bottleneck structure. So it basically has this hidden built-in autoencoder kind of structure, which is the nonlinear generalization of principal component analysis. So basically only the most important elements of the data are learned and then stored, and then from a sample of the source distribution, one samples new samples and generates, according to the target distribution, new samples. Now, this is what was used in the work of Alexei Kondratyev and Christian Schwarz in 2019, their work on the market generator. And it has been working quite well on fitting marginals of the data. They were fitting QQ plots to the returns, and also showing that the generated distribution reflected several stylized facts of financial markets. So later on, we went on with Alexei and Christian to use this restricted Boltzmann machine to demonstrate several use cases and applications of generative models. For example, detecting overfitting and avoiding overfitting, detecting outliers, or even data anonymization. Now, the other very, very important and very popular way of generating models, generating samples, are generative adversarial networks. These consist, I know that many of you already know them and are very familiar, so I will just say very briefly how these work. There is a generator and a discriminator involved. The generator generates samples where the discriminator tries to tell or gives feedback whether this sample is fake, artificially generated, or original sample. And by that, this interaction of the two sides improves and increases the accuracy of the generative model. Now, these generative adversarial networks have become very popular, in particular in image processing, because of their very, very good performance in generating sharp and realistic images. And several of these can be seen in the website. For example, this person does not exist. They generate images that are just astonishingly sharp. And this is in fact their advantage over variational autoencoders. So these generative adversarial networks have been in fact used also for market generators in the work of Wiese, Knobloch, Korn, and Kretschmer, and quite some others, ongoing works as well. So this is the one that I wanted to point out. It's called QuantGAN because it's also targeting the generation of financial time series. Now, in our case, we decided to go for variational autoencoders. And yes, the fact is that for image processing, these have not been too popular. And the reason for that was that they tended to give a bit blurrier images than GANs. But if we think about it in the perspective of generating financial time series, this is absolutely not a problem, because what we want to generate are actually distributions. So it's not the main importance to have them, the images or the outputs, extremely sharp. We have a completely different objective function to target, which I will be speaking about in more detail later. But all of these models are data-driven. They were all used and developed for static problems. And the adaptation of these models to financial time series is really not straightforward. There is one approach to adapt these models to financial time series, and that is by Beatrice Achayo and Piangchang Xu, I hope I pronounced it well, and their collaborators, and this is by causal optimal transport to not only fit marginal by marginal, as was the first approach of generative modeling to financial time series. So in this sense, one extends from fitting marginal by marginal the distributions to incorporating the time series aspect and the evolution over time. But in this work, we take a different approach, and this is by rough paths and signatures. Now, yes, these rough paths and signatures approach to generative modeling was first proposed by Levin, Lyons and B in 2013. And they were the ones to first propose the signature of a path as a basis of functions on path space. Now, what is it? The signature of a path is a series of iterated integrals mapping from path space to a space of tensors. And similarly, the truncated signature is just this infinite series that is stopped at a level, which we refer to as a signature order. So the question is, why signatures? They are similar to Fourier transforms and wavelets in that they are approximating curves as a linear combination of basis functions, but signatures do so in an unparameterized way. And our goal was here to do market generation in an as flexible and unassuming way as possible. So fully data-driven and fully non-parametric. It's also possible to have a model-free and path-by-path characterization of the paths. And if the paths are generated by a stochastic model, then the expected signature characterizes the law of the stochastic process fully. Now, they also have the advantage, and now we're coming to extremely convincing properties of signatures. And that is that they have a certain robustness to missing data or irregularly sampled data. or highly oscillatory data, and they are invariant under time reparametrization. So all of these can be found in the work of Liao, Lyons, Ni, and Yang from 2019. And furthermore, and now we're getting to the part where it becomes quite interesting.
And I stop you for a second. I want to ask a few questions that.
Of course, yes, please.
Time. So there is one question by Perez Arribaz, and he is asking why aren't LSTM networks considered for the time series component of these problems, or are they actually incorporated in the approach that you mentioned?
So we are using a very simple network in our case. What we are using is really the simplest of variational autoencoders that you can imagine. But the reason is very simple. That is that that we have very little data available. I will speak about that later. Of course, this work that I just mentioned here is combining the signature approach with recurrent neural networks. So there is absolutely no reason why not to do that. In our simple consideration and in our scenario, we tried to take care of the time series aspect by signatures. In fact, the two are quite related with one another. So rough differential equations or these recurrent neural networks. So we tried to take care of the time series aspect by using signatures, or in fact locked signatures. And the generative aspect, let's go back just a second. The generative aspect by the variational autoencoder. Maybe just one more sentence to that. So variational autoencoders are very close or building on the idea as autoencoders. So again, they rebuild samples from a bottleneck structure encoding. So that means that they're very parsimonious and they can be trained on very little data. And this was basically our goal, to have a model, a generative model that works with extremely little information. I will tell you in a second why. From our numerical experiments, we were trying to fit data samples that are in the hundreds. So we were fitting, let's say, weekly data or monthly data from the S&P 500, which means that we end up with 250 data samples. In these cases, we really don't have that much of a possibility to play around with too many nodes or complex networks. That's all.
Okay, good. And I have another quick question. For the GANs, generative adversarial networks, have they ever been used to model, let's say, the position of a trader who is competing with the rest of the market from an individual trader's point of view? I mean, can I view the market as my adversary and then I try to like profit off, let's say?
I mean, of course, this is a possible approach, and nobody says that you shouldn't be doing that. This is also an extremely interesting point of view. The question is whether you have enough training samples, because these generative adversarial networks are known to be notoriously difficult to train. Finding and fine-tuning the hyperparameters is really usually a non-trivial task. So you might need training samples that are of orders of magnitude higher than the ones that we were trying to use. That's all.
I see. Thank you. Yeah, please go ahead.
Okay. So these were two reasons for signature. They're robust in many senses. And here we're starting to get to something quite interesting. Signatures provide the right framework for performance evaluation metrics on path space. Okay, well, one of the difficulties being that path space is infinite dimensional and not locally compact. So what do I mean over here? When we looked at first approaches to market generation by fitting marginals, then there were well-established metrics. I don't necessarily want to list them all, but there are well-established metrics on the level of distributions to compare whether the target distribution is close or not close to the sample distribution. For example, KL divergences, Wasserstein metric, or you name it, or even two sample tests. Now, generalizing this to the infinite dimensional case is by no means straightforward. And I will speak about that as well later on, that doing this path by path in a marginal by marginal manner is not necessarily the right thing to do, and highly problematic. So it's very advisable to look for evaluation metrics on the level of the path space, so on the full stochastic process. But then the question is really, how do you say whether two stochastic processes are close to one another in distribution? And when we're speaking about data-driven models, so we're not even in the realm of stochastic processes anymore, but we are really looking at data that comes to us path by path as a time series, then it becomes even more difficult to say how can we tell that two paths are close to one another if we want to do generative modeling. Just keep in mind that we do not want to just replicate the paths path by path. That would be easy. We want to understand the underlying distribution and replicate the distribution that is somehow different from the original one. So this is highly non-trivial, and we will speak about this a little bit more later. Now, in fact, what I didn't say so far is that we went a step further, and as suggested by Liao, Lyons, B, and Yang in 2019 in this very same paper, we did not only take the signature of the path, but we went a step further and took the log signatures, which kind of encodes the same information, has all the positive properties that the signature has as well, but an even lower dimensional representation, so easier to train. And also, it is better suited to the variational autoencoder that we wanted to use. So positive things are that there's a one-to-one map between the signatures and the log signatures. Log signatures have all the positive properties listed above. So they're robust to irregular sampling. So we do not have to set a mesh, but the samples can be relatively irregular, and it's possible to accommodate to that. High frequency samples are also easy to deal with, and so on. One advantage, however, is that if we're putting our samples into a variational autoencoder, and now we're sampling from some kind of random distribution, then doing that on the log signature level is better suited because it's linear space. Okay, so now all the motivation why we do the things we do them, now we can get into what is it that exactly that we're doing. So this slide will give us our general strategy. I will go back and forth in 2 minutes. It will do it in 5 steps. But let me go through all the steps in a second, one by one. So what we're interested in are several things. One of the things that we're interested in is, how does this signature-based or rough path viewpoint compare to the marginal by marginal kind of learning? in terms of accuracy and how many samples do we need and so on. So for that, what we do is we take the original data series, which, for example, let it be the daily data from the S&P 500 index. So in this situation, it's just one-dimensional. And keep in mind that if we're looking at the S&P of the past 20 years in daily data, we're roughly at the value of 5,000 daily data points. So this is really not much to begin with. And this data we're dividing up into three aspects. One is the daily data. This should be a 2, so I apologize for that. Counting is jumpy these days. So the second one is weekly path segments. So that means we're taking 5 business days. And then the third one is monthly path segments. So here we say, okay, 20 business days. So these are the three aspects that we're looking at, and we are both in the second step pre-processing the data in 2 ways. Here, number 1 and number 2. We're taking the returns, so daily returns, weekly returns, and monthly. So for all of these path segments, and taking the log signatures, but obviously only for number 2 and number 3, so where we actually have a path available. And in order, I do not want to go too much into detail of that, but in order to accommodate for the importance of the volatility aspect, we take a lead-lag transformation of the paths, but you can find all that in the paper. So this is what we do as the pre-processing of the data. Now in the second step, maybe just before we go to the next step, let's appreciate that in this situation when we're really taking 20 days of paths, we are in a scenario where we already have only 250 sample paths available at that moment. And now we're using that to train a variational autoencoder. So yes, we're choosing that because it's parsimonious and with a bottleneck structure. And we're going even a step further. So we're not only trying to get to model the distribution of the process in terms of sample paths, but there's one difficulty of financial time series that I have not mentioned so far elegantly, and this is the fact that financial time series is not stationary. So there is actually a necessity to condition on current market conditions and be able to generate sample paths that are somehow conditioned on the current market conditions. And what we chose to condition on are the current level of the index, or the current instantaneous volatility, or number 3 is the signature of the previous path segment. And C, so the third one, turns out to be quite useful. I will explain that later, in order to not only generate weekly or monthly paths, but being able to patch them together into longer paths than that. Keeping in mind that we are dividing up the data into path segments of weeks or months, we're not really addressing the problem of non-stationarity of the data. We are still using historical data somehow to learn the distribution from the paths, and by no means are we going to be able to predict extreme events like now from historical data. So this is a challenge that still needs to be addressed in the future, but I will leave that to the end. So in any case, to address the conditionality or the non-stationarity in some way, we also train conditional variational autoencoders to to current market conditions. The output of the variational autoencoders are again on the level of signatures in the case number 2. And it's on the level of returns in the case number 1. So this has to be post-processed in the sense that this has to be transformed back to paths. In the case when we're generating returns, this is easy. In the second case, when the output are signatures, this is really actually a highly non-trivial task that is being addressed in several by several people in Terry Lyons' group. What we do here is a relatively brute force evolutionary algorithm that can also be found in the GitHub if you want to take a look at the paper.
Blanca, let me interrupt. You have 5 minutes.
Yes. Okay, yeah. I'll be fast from now on.
Yeah,
so,
5 minutes.
Okay, so now we speak about performance evaluation, but we spoke about it before. The question is really, what are good performance evaluation metrics on the level of sample paths? Now, here are some numerical results. First numerical result is right there. Signature-based training, so this number 2, is at least as accurate as returns-based training, and in some cases even more accurate. What we see over here are projections of the signature map to different dimensions of the truncated log signatures. And on the right-hand side, we see in final distribution of the generated paths. So in either case, one can translate, of course, if we generated some paths via signatures, then we can do the same thing and translate them into returns and compare them on the level of returns. Or if we have generated returns and built some paths out of them, we can also take the signature of that and compare those. So that's how we compare the two with one another. Now, another numerical result is the following. It's observed in 2 ways. So the signature-based generative model works already well with a low number of training samples available. So on the left-hand side, we see an image of weekly paths, which are roughly 1,000 samples, so trained on roughly 1,000 samples. And on the right-hand side, we have monthly paths, and both seem to be working quite well. And we made another experiment where we are increasing the number of samples by numerically generated data. And now this is not very surprising. We took a rough volatility model to take numerical paths that exhibit the autocorrelation and more complicated effects. And what we see is that if we increase the number of paths, the performance does not necessarily increase. So we can be quite happy that the performance already works quite well with a small number of paths. Now here it is. Once we evaluated on the level of signatures, and here is how it looks when we transform back to paths. Now, one thing I would like to go into, if I have very little time left, is this. So by conditioning on current level of the index, instantaneous volatility, and number 3 was the signature of the previous path segment, we can patch together paths in a consistent way to generate longer paths than the direct output of the process. So the direct output would be weekly paths. We can patch together 4 pieces and get a monthly path and compare that directly with the output of the monthly signatures. And we see that there is quite a good consistency between the 2 of them. And we can use exactly the same methodology to go beyond 1 month and go here. What we see are yearly paths generated, but there's no reason to stop at yearly paths. So this is actually good. And maybe another comment is that if we're doing conditioning, of course, the number of available training samples becomes even smaller than originally. So it's quite crucial that the network is robust and parsimonious. Right, maybe these two last points on what are good performance evaluation metrics. I have mentioned that real quick before. For classical models, typically one would want the model to reflect as many stylized facts as possible, maybe fit option prices very well, or be able to consolidate between different markets, and then we would consider that as a good model. But one crucial observation there is that these are continuous time stochastic processes. And now when we're speaking about generative models, there we have although we think we have much more flexibility, in fact, there is a limitation that in the target distribution, we have a predefined time grid on which we can observe samples. And if we're only observing these marginals or these samples on this predefined grid, even if we manage to fit these samples as closely as possible in the P measure, even indistinguishably well, there is still quite a lot of freedom what we can do in the Q measure. And it can become problematic. So I would... yes.
Don't interrupt too often, but you should wrap it up, let's say another minute or so. So that we leave for questions. I think there are a lot of questions for you waiting.
Oh, okay, that's good. Yeah, so I will refer to these two articles by Damiano and collaborators underlining the necessity of this pathwise evaluation. We have spoken about the difficulty of doing that. All right. The last point was to say, why is this even necessary? Well, it's necessary for the following reason. If we want to train the deep hedging engine, we would want to train it on data that is as realistic as possible. And ideally, we would want to train it on available market data, but if the available market data is as it is over here, 5,000 data points, it's not going to be enough. So one would like to have market generators that have a high quality of training samples. And market generators can address these issues of data availability, data privacy, so if we cannot use actual data because it's proprietary, or if the data quality is problematic. But in general, we will need some standardized and widely accessible testing data sets for such machine learning problems, such that we can promote innovation. That's all I wanted to say, and thank you very much for your attention.
Okay, great, Blanca. Thanks for the talk. There are a lot of questions. Let me start with one by Romuald Lee. He has asked actually several questions, so for purposes, I will only pick one of his questions, unfortunately. And well,
maybe he can turn to me afterwards directly.
Oh yeah, he can follow up with you.
Yes.
So I think I took one question that I liked. He said, "Why don't you think it's way too dangerous to create data-driven market simulator, which at some point will be combined with data-driven reinforcement learning algorithm, leading to blind and non-explainable trading strategies, and possibly provide an extreme systemic market movements which cannot be explained?"
I think, okay, it's a tricky question, isn't it? Well, thank you for the question. I think the key is really to be able to assess the risks. And that's why I think that this point 1.5, and this is why I emphasize that so much, being able to use our knowledge about models, parametric or non-parametric, be it signatures or not, that will be key. So Of course, it would be dangerous if we're not able to assess the risks, but hopefully we can do it in a way that we understand what we're doing.
Yeah, good. So there is another question by Qi Feng. He's asking, can you explain the mesh free you mentioned before? During your...
Right. So what I wanted to say there is that is consistent with respect to sampling. It's not, I mean, mesh free is not quite right, because of course you have to sample, and sampling is always discrete. But the key here is that it is consistent under resampling.
I see. Good. Okay. Question from Bill G. Hilmas is why did you separate the data into training and validation? And if you did that, what's the result for the validation part? Or what's the out of sample performance, I guess?
So what I didn't quite get into in detail is how do I evaluate the out of sample performance? So I did not even write down the this two-sample test that was proposed by Harald Oberhauser and Ilya Chevirev. Of course, the data was evaluated and out of sample. The way it is evaluated is the following. We have this two-sample test, and we want to evaluate it on a level of such and such confidence level. So usually we would say 99% confidence level. Is this two-sample test able to distinguish between generated samples and original samples? And that's how we evaluated.
Okay, so you did that.
Yeah.
And question from Josef Teichmann. He's asking, how do these generative models compare to classic econometric models? And which tests have been performed? Comparing with the state of the art.
Classic econometric models or stochastic models, or?
His question is like classical econometric models. I guess he means regression or different variations like of regression techniques.
If we are comparing these to market data directly, I mean, the flexibility that's added is just immense. So this is in several aspects much better. Classic econometric models have the limitation that usually they are predefined on a certain grid. We also tried it out with a rough volatility model, in fact, but what we say is, if we're trying to fit a rough volatility or a classical econometric model to historical data samples, it's kind of an unfair comparison, because we would have to take several regimes of model parameters to fit these kinds of historical paths that we observe in the past. That there's no guarantee that the model remains the same with the same chosen parameters over time. So it's kind of an unfair comparison.
Okay. Okay, I think there are still few questions coming up. There's a question by Mauricio Elizalde, who wants to know in which paper we can find the 5 steps of the general strategy.
Oh, I will post you the link to the paper afterwards. It will be on archive in the next few days.
Good. And okay, final question by, let me pick Romuald again. When we feed a generator, a GAN or VAE, with a simple synthetic time series, let's say a discrete Brownian motion, how does the output returns succeed the normality tests?
Can you repeat, please?
Yeah. So if we feed a generator, let's say GAN or VAE network, neural network, with a simple synthetic time series, a discretized version of the Brownian motion, how does the output return succeed the normality tests? So if you do a normality test on the output returns, does it succeed?
So we I have to admit that we did not do the normality test. We did several other tests, but one of the tests we did was basically this test with a rough volatility model, which is similar in nature to the question that was asking, and it performs very well. So it is indistinguishable. Now, if we also tested that out with Kolmogorov-Smirnov tests. Now, I'm fairly confident if we're looking at normality tests, we can get the same result. But I have to admit that this is not something that we did, but we can do that.
Okay, question from Krista Cucchiero. What performance metrics do you use, and is this on the level of the distribution of the generated signature?
We try several. So we try. First of all, this performance metric proposed by Oberhauser and Chevirev.
Yeah.
Just 1 second, right there. And which can be found in this paper. This is the one that's being implemented, and that is consistent to sample tests on the level of the path space. But we also tried a few others on the level of marginals at final time. And yes, so we try to be thorough.
Okay, good. Yep, I think I don't want to, maybe let's take just another extra question from the audience, and then we will session. There is a question by Boris Davidov. How many real-time testing were performed? And real-time, it means with the real data as well. So are your tests based on synthetic data or the real data?
So both. The point was to do it on real data, on a couple of market indices, but we also tested it on synthetic data. But the point was to do it on actual data. That was the real main difficulty.
Okay, good. Okay, so then just to be on time, I would like to thank Blanca again for giving a very interesting talk. Like, I certainly learned a lot, and I'm sure that the rest of the audience learned a lot as well. It's good to see how many people in the community are working on these topics as well. And before we close the session, I would like to mention that there will be a talk on May 14 by Bruno Dupir. It's the third talk of the online seminar series that we started. And this talk will be on the geometry of money and the perils of parameterization. So it's a very engaging title. And I also want to mention that all the information about the online seminar is being posted on the wiki page of the SIAM Activity Group. And Igor has sent an email with the distribution list. So you will have all the information you need to access the wiki, and you can see both the past talks and also the upcoming talks. Okay, and with that said, I would like to close the session for today, and looking forward to the next seminar series, to the next seminar of the series. Yeah, thanks all for attending.
Thank you very much to everyone.
Special thanks, Blanca. So,
thanks, Blanca.
Thank you, Blanca.
Thank you.
Applause, but unfortunately cannot do that here. But I'm sure many of the other participants will follow up with other questions. I'm sorry that I couldn't take all the questions from the audience, but we cannot go out of time.
Thank you again.
Thank you again.
It was a real pleasure. Thanks a lot. Have a nice evening.
Thank you.
Bye.
Bye.
Thank you. Bye.